Okay, so let's start. So from next week, we are going to next week we are going to have a lab session. So this is mainly based on the what we have learned from the past 6 weeks. I mean, including today. So in the lab session, also I going to have some lectures first, and then we can do some labs about the machine learning for the classification. So week 8 it's going to be a cross-book midterm. So midterm is mainly based on from week 1 to week 7. So we have some very general questions and also have some calculations based on what we have learned from today. Um, After that we are going to have like 1 to 3 weeks for because today we are going to quickly go through about machine learning. Okay, the traditional techniques like for the classification stuffs like regressions, linear regressions and nonlinear regressions. And also today we are going to have a little bit equations because we need to understand how to optimize the models. So later on 3 weeks for the learnings, and later on we have two. Okay, this week there's no lectures. We're going to have 2 weeks for the presentations and also make our class. I will collect your preferences in terms of the time. So any questions? No? Yes, assignment will be roughly next week. Yeah, because I need to finish this week. Okay, this week going to have some equations, have some calculations. Okay, the keyword for today is the machine learning. Okay, I'm going to introduce several parts. I mean, including the most typical machine learning techniques like linear regressions and the logistic regressions. And later on, I'm going to introduce the decision trees. So decision trees is another rule-based, okay, machine learning techniques for the classifications. And later on, we are going to, I mean, for each of the methods, we are going to have okay, in-class practice to let you know how to achieve this machine learning techniques. And later on, we are going to, okay, we are going to several page talking about the overfitting problem. Okay, this is a typical the bottleneck problems for the conventional machine learning techniques. So this is roughly for today. And during the class, okay, we are going to have some derivations because, for example, like the regressions, okay, there are some parameters we need to estimate. So before I start, I wish to know any of you have done the gradient descent before? For example, if you want to solve the nonlinear, okay, nonlinear cost function, you need to do the gradient descent. No? Okay, no problem. Okay, I will make this in from scratch. Okay, the same. So we have quite a few TAs. I always encourage you to raise the issues from GitHub if you have any questions in terms of the code. So because I mean during the class we teach a lot of things as well. But if you want to learn more, okay, you can try like for example today we talk about the machine learning with linear regression and the logistic regressions. We provide some examples, right? So if you want to have a better understanding, of course you can try more examples, especially for the logistic regressions. And later on we have the decision trees. You can try more examples as you wish. You need to learn with extra time. So in terms of assessment, so this is what you should be most interested in. So we have 2 assignments, and the first assignments will probably be next week. We finish the content for next week, and we will release the first assignment. But don't worry, okay, the assignment is not difficult. We include some general questions and some calculations, and the calculations is all, I mean all the content is included in the lecture notes generally. So midterm quiz test is like 15%. Okay, group project. Okay, roughly we have like 14 students. Okay, so maybe one of each of you need to make a presentation. So final exam is going to be open book. Open book is general questions and some calculations. So for today, okay, because I mean, so in the past week we focus on the unmanned autonomous systems. We quickly helps you to recall what we have done from the first week. So today we are going to talk about the outlines, including the regressions and the decision trees and the random forest. Okay, and the random forest. Okay, quickly go through random forest. So in terms of the classification, so this is the figure we have like provide with you in at the very beginning of this course. So generally, the artificial intelligence is on top. Is on top. There's a program that can sense, reason, act, and adapt. So in the middle is machine learning. Okay, it's like it's a story in the past like 14 years, 40 years. Okay, 40 or 50 years. Machine learning, we have some names like random forest, decision trees, and also regression stuff. So those are all machine learnings. But because you all know the deep learning is so popular, right? But still we need to understand roughly what happens in the past and why we need to have deep learning. Because I introduced the decision trees first, like all the machine learning to you, and then move forward to the deep learning. You will know why the deep learning is so powerful. In this case, you have the differences, right? You have understanding of the differences between those machine learning and the deep learning stuffs. And machine learning is actually a method to achieve AI. Okay, it's a method to achieve AI. So deep learning is actually a technique for implementing AI. Okay, implementing the machine learning. So roughly, I mean the differences or relationship between those three keywords is like this. So, but at this moment, if you talk about machine learning or AI, everyone is thinking about deep learning. Everyone is thinking about deep learning. Okay. So generally, the green part is actually, I mean, one of the focus of this course, deep learning. So later on, like if I have time, if I have time, I will also wish to have one more lecture to introduce the latest, the principles behind the DeepSeek and open and the like ChatGPT if I have time, because the deep learning is currently the most state of art. So if you look into the categories, machine learning can have the supervised learning. It means you have the labels, right? If still can remember. So the semi-supervised learning means some of the data you don't have labels. Some of the data you have labels. So unsupervised learning means you have no labels, no labels. Okay, it's mainly based on the clustering. So today we are going to talk about the KAN. It's a method to do the clustering. So for regressions, we have logistic regressions and linear regressions. So this part is actually is the old techniques, but currently it belongs to usually make this belongs to the deep learning part, because it's kind of like related to the neural networks. So regression analysis. Regression is mainly used for the classification or the prediction. For example, predict the prices of the horse. Okay, under this very complex economic period. Okay, for example, to predict the house prices. So regression for classification is approach where regression techniques are adapted to solve classification problems. So later on, we are going to have examples. So the key concept is regression is it's a continuous process. And classification is, for example, prediction of the house price. Okay, it can be a continuous value. For example, the house like 100 meters square can be 2 millions of HKD. So this is can be 2 millions, 3 millions, but for the classification problem, it's only binary results, 0 or 1. Okay, it's different. It's mainly like binary results. So as mentioned, so regression includes the predicting a continuous output. For example, like predicting the prices of a house. For example, based on the history data in the past 20 or 50 years, okay, we can predict how the house prices will change over time. And if this is not good enough, we can combine the history data from Japan to predict the one from Hong Kong, because history is always the same. Its history is very similar. So this is part of the regression. So the classification is includes predicting a discrete label. It's a binary result. It's like 0 or 1. It's a binary result. So for example, determine whether an email is spam or not. Okay. So as I mentioned in the very beginning, in the first week, we talk about the classifications of spam or non-spam emails. So for a regression for classification, so the idea is to use a regression model to predict a continuous score. Okay. For example, like if the score is more, if the probability is more than 0.5, it may be yes, otherwise it may no. So logistic regression is a discrete discrete output. For example, the output from logistic regression is 0 and 1. This one we can say like regression is linear regression is like from 0 to 1. Okay, later on we're going to have examples. So the major difference is this one uses a logistic function to model probability that a given input belongs to a particular class. So the major difference is this is 0 and 1. This one is from 0 to 1. So let's start with the examples that for the linear regressions. Okay, start with the examples for the linear regressions. So from the name, I mean the linear regressions. What is the first thing appear in your mind? The linear regressions. This means the relationships between the dependent variable and independent variable is linear. For example, y equals to ax plus by plus z something. So let's know exponential components. Let's know quadratic functions, quadratic components. So this is the linear. For example, like based on different features. For example, different variables, we can have a single variable regressions. So y equals to fx. And for the multiple variable regressions, it means usually have multiple variables, right? So for example, if you want to predict the prices of a house, okay, you need to consider the multiple informations, like the location of the house, okay, the time, the date, okay, the area of the house. So those are different variables, right? Can be equivalent to corresponding to x1, x2, x3. So for the functional relationships, we have linear regressions. Okay, like okay, y equals ax, because relationship between x and y is a linear, okay, linear. So of course we can have the nonlinear regressions. For example, for some very complex relationships, the linear case is not good enough. So we need to have nonlinear regressions like kind of ax square. Okay, if you have the square or exponential parts, so this is going to be a nonlinear case. Nonlinear case. So let's summarize. So based on variables, we have single variables and multiple variables regression. And from the relationships, we have linear regressions and nonlinear regressions. Okay, so let's see the examples. Like the first one is a nonlinear case, and right side is a linear case. So for example, if you wish to use the height, okay, use the height to predict the weight. So let's, for example, you can based on those points, the points means data. X is the height, and this is in centimeters. Okay, so this is the weight in kilograms. So generally, based on those data, you can fit a line, right? So based on this line, no matter how many data you get, so for example, if you only get the data from 160 centimeters, you should able to predict, okay, the weight of the, if the, x-axis value is like 2 meters, okay, 2 meters, you should able to predict the weight. So this is the linear case. Of course, you can use a nonlinear curve to match fit those data, fit those data. So this process is called data fitting. The left side is a nonlinear case is okay, the doctors per million people, okay? So it means more doctors, generally we should have like high expectations in terms of the life, right? So for example, the x-axis is a number of doctors in value of million populations. And the y-axis is life expectations. You see, if the doctor is quite limited, okay, this is, highly related to the number of the doctors in terms of the life expectations. But if the number of doctor is kind of good enough, okay, the number of doctor is not going to be the dominant factors because it's good enough. Okay, it may be affected by other factors. So this is a linear case, and the right side is a linear case. So mathematically, if you want to fit those data, so this is an example. This is naive examples for the linear and the quadratic functions, right? So later in practice, the problem can be much more complex. For example, like in here, we only have two parameters, right? So in the practice, maybe like parameters number can be reached like 10 or 20, it's possible, but generally it's similar. So for a linear case, okay, y equals to ax. So a is a curvature, or call this is gradients. And the example of distance and speed. So this is a linear case, right? So based on speed, you can calculate the distances. So the second part is example of distance and accelerations, like y equals to ax squared plus bx. So because we have the quadratic terms, that's going to be a nonlinear case. So the example is the distance and how the distance is related to the accelerations, and this is the initial guess. So this is an example like I just mentioned about the house prices. So if your house the area is like 100 square meters, and if we say if the prices is like 1.5 millions, so this is a good investment. So the good investment means for example, the value is more than 2 millions, but you buy it like 1.5 millions. Of course, this is a good investment, right? So this left side is the data. So left side is the data in terms of the areas. Okay, this is data from like 80 square meters. Okay, 79 square meters from 90 to 100. Okay, more than 100. Okay, this is right side is the prices. Okay, right side is the prices. So based on those data, for example, okay, from 1, 2, 3, 4, okay, you get the data. So, okay, can you predict if, can you predict this values? Okay, based on this data and this data, can you predict? Okay, so this is a very representative examples like how to use the existing data. Okay, so for example, okay, if you based on all those existing data, you train the based on data to get the curve. Okay, the line fitting, get the curve. Okay, this is the parameters of the model. So based on this model, you can predict any values. Okay, to get the then you can get the values of the cost, the prices. So first, we can establish the relationship between the A is the areas, right? The function FA, A is the area. So P is the prices. You can generate or establish the relationships between A and P. So A is the area and P is the prices. So you can predict the prices, okay, based on relationships. So based on this up and down data, okay, to predict the model. And let's you can evaluate, for example, if based on this prediction, if this value is large, much larger than okay, 1.5 millions, it means this is a good investment. Okay, so the principle is like based on the existing data, okay, put the data in the plot. Okay, try to find a line to fit those data. Because the majority of the data, they should follow a specific phenomenon or specific functions. Okay, in this case, you can fit a line. So PFA, A is areas, right? FA is a function mapping from area to the prices. Okay, to get this function, you need to calculate A and B. So this is the very naive examples of the machine learning. So A and B is the parameters of the model, and this is the model, the representation of the models. Okay. So based on those data, we can like represent the data, the function with different parameters. For example, if we set the A and the B with different parameters, right? So we can get a different curve. Of course, I mean, for different A and B, so the accuracy of the fitting is going to be different, right? It's going to be different. So how to evaluate the good or not the accuracy of the model is, of course, it's going to be the distance from the point, okay, to the line, right? Distance from the point to the line. So for example, if, okay, this is area, okay? So for this one is area, the same problem as the previous page. So this is the cost or the prices of the house. So if A is 0, okay, A is 0, it means B is 10, it means Y equals to 10. So this is a straight line, right? This is going to be a straight line. So of course, for the first one, the fitting is not good because I mean the distance from the point to the line is kind of large, right? So for the second one is much better, right? So if A is equals to 0.1 and B is equals to 0, and for last one is it's like okay, I mean it's not good fittings, right? Because for those points, so the points to the line is much larger compared with the middle figures. So how to evaluate the goodness or the accuracy of the line fitting is to evaluate the distance, okay, between the predicted values and the exact values. So for example, X is the model input, X is the model input. So X is I mean the values of the area, values of the area of the house. So yi is the true values. The true values is coming from the previous table, okay? Okay, the yi is the values coming from this columns, okay, the prices. Okay, this is the non-variables. So yi is the model outputs. For example, if you find the A and the B parameters, right? So for any given X, you should predict yi dot. That's right. So for example, if A is equals to 0.1, B equals to 0, you should get the yi, okay, based on the X. So M is the sample size, means how much data you have. So yi is as close to yi dots, it's as close to yi as possible. So this is predicted results. This is predicted results and the yi. Okay, this is the true pose. So the physical meaning, okay, the physical meaning of the so the physical meaning of this function. So the yi dot minus y is the distance from the line to the point. From the point to the line. Okay. So let's represent the distance from the point. So for that advance, the distance is infinite. Advance the distance, the condition of the distance is infinite. So that's the function of the A and B parameters is the optimal parameters. Okay, so the objective is to minimize the distance from yi dot to the yi. So yi is a true pose, right? So any questions for this one? Good, right? Good. Okay. So, okay, let's look into this problem in detail. So the function of the straight line can be represented by A is the curvature, right? So B is the values of in terms of corresponding to the offset. So y equals to x plus b. So if you want to find this line function to base the fitting those points, okay, you need to calculate A and B, right? You need to calculate A and B. So the solution is to minimize. The solution is to minimize the summation of the distances from I plus I equals to 1 to m. M is the number of points. Okay, to minimize the distance, summation of the distances. So to minimize this, it's going to be the m is this one and this one is, I mean, the solution is going to equivalent because for a given function, if you minimize this one, multiply the given coefficients it will not affect the solution. So M is the number of points. So to minimize, for example, this is to minimize the summation of all the distance. So this is to minimize the average distances, okay? Because the number is, the M is the number of points, how much data you have in this data fitting problem. So in this case, I mean, if you get this model based on this function, you should be able to find the line. You can predict any data. Okay, for example, like 2.3.0 meters, you get you should like, okay, so this area, like 300 meters square meters, you get the prices. You get the prices. Okay, so this is a very good example, right? So if I have a series of data, okay, if you look into the left side, okay. Okay, look into the left side first, okay? So X is like 1, 2, 3, right? 1, 2, 3. Okay, you get 3 points. Okay, get three green points, right? Okay, so X is 1, 1, 2. Okay, of course it's like Y equals to X. So this is base functions, right? So if we select, for example, if we use this function or this function to fit the points, okay, to fit the points. So we are going to calculate the distance, get the distance from the point to line, okay? That's going to be the summation of all the points. Because M is 3, right? Because you get 3 points. Okay, M is 3. So from left side X, Y, okay. So YI is, it's like, for example, if you use the first function, Y equals to 0.5X, so this one is like 0.5, right? And for the second one is 1.5. And this is distance. Okay, so this at 2 multiplied by 3 is the number of points. So finally, based on the first function, okay, based on this function, okay, the summation of the distance is like 0.5. So for the second function is G2. Okay, G2 is, okay, the blue straight line. So this distance, the summation of the distance is going to be like, this number of points is 3, and Y2 is 4. So 4 is coming from minus, is like negative X plus 5, okay? So in this case, if you can calculate the square known distance, okay, square known distance, this one is 1.8. It means the first model is much better because the square known distance is much smaller. So this is a tall example. Okay, it's clear? Okay, so from the general way, okay, the general way. So if you find the line, and if you want to find the base A and B, so you need to minimize this function. Minimize this function. So okay, from the top. So M is the number of points. This is the same as this one. Okay. So M is like how much number of points you have. Okay, M is the number of points. So yi is the predicted value. Okay, predicted value based on your model, So the yi is the true values. This is true values. Because what you get is xi, yi. So the predicted values can be obtained by axi plus b. Because the model you use is a linear models, right? So it means the cost function is the summation of the distance of all the points to the line, okay? So this actually is a function, okay, related to A and B. Related to A and B. So J is the okay, corresponding to the summation of the distances, right? So any questions for the first equation? It's good? Okay. So the problem is when you get to this function, okay, get to the first function. So how to solve it to get the A and the B? For example, okay, previous one is A is this is example. So of course we know the baseline fitting is y equals to x, right? So how to find y equals to x means A equals to 1, B equals to 0. So how to find the line? Especially when the data is like quite noisy, okay, quite noisy fluctuating around the line. So how to find the A and the B? Solution is the gradient descent. So gradient descent is is the most conventional but is quite efficient solution to calculate the least square problem or calculate the optimization problem. So calculate the gradient of the loss function. So loss function is J. So gradient means the curvature of the given point. For each parameters representing the slope direction at the present parameter value. So the slope is the curvature is, for example, okay, this function GAB. So A and B is unknowns, right? Okay, this is a variable that change over time. So also A and B is the one we want to estimate. So find the minimum values. Okay, so by minimize the J function, we should be able to find A and B. Right? To find the minimum values by adjusting the parameters A and B. For example, at the beginning, you have no prior knowledge about how to choose A and B, but you can just provide the initial guess like set A and B is 0, and gradually descend, follow the slope or follow the gradient to gradually approaching the minima solution. So J is FP, okay? J is FP, okay? So in here, P is corresponding to A and B, okay? So this function is the same as this one. So the P here is, okay, just for simplification, P is equals to A and B, okay? So P is a 2-dimension, okay? So P is corresponding to A and B, so 2-dimension. So the gradient descent is due to iteration. So the next iteration is equivalent to the last iteration, okay? Minus, is this a learning rate, okay? Corresponding to the partial differential of this PI. So let me explain a little bit how to understand this equation, okay? This is the example, okay? So for this function, if you want to find the minimum points, of course we know, okay? I mean, for this function is 2, right? Okay, at the beginning, if you look into, okay, I mean, the minimum solution for this function is if x equal to 2, this y equal to 0, right? But I mean, the computer, they don't understand what, I mean, they cannot directly look into the figures, look into the plots. So how they solve this equation? I mean, for example, how to find the x to make the y to be minimal. So the computer don't know what to do. So the solution is a gradient descent I just mentioned to you. So for example, first of all, you can define a J is equal to FP. So P is the same as the X, okay, the variables. So 3.5 P squared minus 14P plus 14. So first of all, okay, because at the beginning we have no knowledge about what is the base X. Okay, the X is equivalent to P here. So we can just set P to a random number, like 0 or 0.5. Okay, we set a random number. So if, and you can set the alpha to a very small number, this can be like 0.01 something. So generally the alpha is set from like some number like from 0 to 1, okay, from 0 to 1. So after the first step, okay, actually you need to calculate gradients. Okay, gradient is like this. For the second variable, is like this. And after that, you can do iterations. For example, the first iteration is like PI is like 0.5. So the next iteration is like initial guess plus the learning rates. Okay, plus the gradients. So the physical meaning for this one is like at the first iteration. So you see, the first iteration initial guess is 0.5, right? It's kind of something like in here, okay? So the first point, okay, is 0.5. It's at this point. So after you do one iteration, okay, it's going to be approaching a little bit to the optimal solution. So for the next iteration, it's going to be approaching 0.6. And if you do one more iteration, okay, it will be gradually approaching maybe this point, this point, this point, this one. Okay, finally it will converge to the this point. So the whole process is so the whole process is like this. It's directly to the equation, okay? Directly to the equation. Okay, equation to this point. So then this kind of makes the digital meaning is behind this function. Okay, so the function is what we need to optimize is J equals to FP. So the P here is equivalent to the X, okay, equals to X. So equals to 3.5 P square plus, sorry, minus 14 P plus 14, okay. So of course we know, so the optimal solution is optimal solution P star is if P equals to 2. Okay, if P equals to 2, the problem solves, right? So this is the optimal solution. But if you give this problem, so the problem is like given the, for example, okay, so let's see equation 2. Find value P star to minimize J, to minimize the J. So the problem is like this. So given a function, how to minimize the J, right? So this is the problem, a definition problem. So if you give this problem to the computer, okay, he cannot plot the figures, he cannot directly look into the figures, right? So because for example, okay, you can directly get the solution x or p equals 2. This is because the model is quite simple, okay? For some complex figures, complex functions, you can even cannot plot the function. For example, if the dimension is more than 3, you cannot visualize the plot. So it's almost impossible to directly get the solution. So the gradient descent solution is like the first step, okay? You need to understand the problem. So for any of the function, I mean, okay, let's read the example, okay? This is x, this is y, for any of the function. Okay, maybe fp is the same, right? So for any of the function, so directive we can look into, I mean, we only have a minimum points for the quadratic function. It's the point that the gradient equals 0. But for different, I mean, but this method is not general to all the problem. So what we can do is we can set the initial guess. Okay, for example, okay, P1 equals to 0 or 0.5, okay? For example, in a slide, we set the P0, I mean P1, okay, the first initial guess to like 0.5, okay? Okay, I just, yes, because I have no prior knowledge about this one, okay? This means 0.5 is kind of like maybe this. Okay, you can, based on this value, you can calculate the f 0.5 equals to. So this is the functions, right? This is the values corresponding to this one, okay? F 0.5. So this is the values. So at the beginning, I don't know this is I'm not sure if this is the minimum value or not, okay? But for any of the quadratic functions, okay? For any of the quadratic functions, I can calculate the tangent line. For example, in the mathematical one, you should have done the Taylor expansion, right? The Taylor expansion. So for the quadratic function, it's a nonlinear function. It's a nonlinear function. So if you do the Taylor expansion, so locally it's going to be a linear function. So for example, for the Taylor expansion, the physical meaning is so given a function fx, okay, at a given function position x should be equivalent to x0 plus x minus x0. Okay, so this is a first order of Taylor expansion, right? So it means you try to fit any of a value based on the given point, okay? Let's say distance from the linearization point means the point you do linearization, you do a Taylor expansion. So this is the curvature. So this is the first order of Taylor expansion. So if you get the f, so the curvature of this line, okay, is represented by fx. So I mean the curvature of this line is represented by fx, right? Okay, the curvature, for example, tangent theta is equivalent to fx, f dot x, the curvature, okay? So the interesting thing is the negative direction, the negative direction of this line, the negative direction of this curvature is pointing to the minimum value. I mean, if you are talking about the quadratic function, so that's why all the problem, for example, if you do the optimization problem, so all the problem, finally, okay, researchers will, I mean, transfer the problem to a quadratic function. Because for any of the quadratic function, it always have one minimum points. And the gradients, the negative gradients or the opposite directions of gradients is pointing to the minimum points. It's pointing to the minimum points. So in this case, based on this initial guess, can we directly go down? Okay, can we directly go down based on this direction? Okay, to gradually approaching the minimum points. Okay, so this is how the equation coming from. If you look into the slide, so the slide is P2 is equal to P1 minus learning rate. Okay, the learning rate is, for example, in here we select the learning rate as like a very small value. Okay, a very small value. So for example, okay, so the next iteration is equivalent to the previous iteration value minus learning rate multiply the gradients, multiply the gradients. Alpha is the learning rate. Okay, multiply. So the gradient at the previous point, P1. Okay, this is P1. This means you're going to, okay, going down. Okay, going down from the initial guess from 0.5. So for example, if you do this, it will go to this point. Okay, so this can make sure the J or the F is getting smaller and smaller. This can make sure because you are going down with the negative gradients. Okay, negative gradients or negative directions of the curvature. This can make sure you are getting smaller and smaller. Okay, so for example, okay, let's do one more iteration. So the P2 should be equivalent to P1 is 0.5, right? Plus, sorry, minus For example, if we select alpha is equal to 0.1 something or 0.5, okay, you can select any value as long as the alpha is ranging from 0 to 1, okay? So usually the alpha is ranging from 0 to 1, okay? Multiply f dot p1. Is that correct? And for this function, the f dot x is equivalent to 7 multiply p minus 14, right? So in this case, for this function is equivalent to 7 multiply 0.5 minus 14. So the p2 is going to be 0.5 minus. So in this case, so the p2 is going to go to the next point, okay? Go to the next point. So this point is going to be from this point, move to this point, kind of this point. Okay, the value is equivalent to this one. So you, based on the P2, okay, based on the P2, you can do the next iterations. So based on the P2, you can do the next iterations, okay? Get a P3. P3 is equivalent to the P2 minus alpha, Fx P2. So the P2 is this values, right? You can calculate the P3. P3 is equivalent to, it means you gradually, you do one more iteration, you go down again. So this going to be, okay, this going to be moved to the next point, maybe at this point, okay? So you can do this calculation. So the physical meaning is you calculate the negative direction of the linearization and go down, okay, gradually. So the learning rate, the alpha, it represents how fast you go down. Okay, if you set the alpha to a very big value, it will go down immediately, but it will fluctuate. So usually we set the value experiential value is like 0.5 or 0.6 something, okay, to make sure it's gradually decrease. So the solution is called gradient descent. This can be used to solve any of the Cauchy function. Okay, so please take try. Please take try. So based on this, okay, you can look back to the slide. Okay, please do it. Okay, and solve the p, solve the pi here. Okay, so the optimal value should be 2, right? So after you do the like around 3 or 4 or 6 iterations, so the value of p should be kind of very equivalent to the 2. Okay, take try. 10 minutes. Okay, if you wish, you can follow this one, like P3. Okay, P3, the P2 is coming from here. Okay, put the P2 to here. P2 get the P3, right? The next step, do the same. Also let me know how many iterations. as I said, okay. So for example, this is output of model, and system is system output. And well, we do that from scratch. So that's like if visualize the process, visualize the process. For example, okay, visualize the process means. So visualize the process means, for example, that's the list you need to plot a function, and let us know for each of iterations is like what is your, your process. For example, P1, P2, visualize the P1, P2. So system, visualize the have a function. Okay, take break for 10 minutes.